Greetings, Saintsmen. We're live for section 2.2 regarding inductive and deductive reasoning. So far, we've actually only explored inductive reasoning. And when we left off yesterday, we were exploring this equation right here, where we had the number times uh, the previous number of the term, which we described as s sub n minus 1. And we were discussing Carl Gauss and how he was able to get uh, the summation done for a number of numbers. It was the figurate numbers, so 1, 3, 6, 10. And what we did is we added the previous term by the next number in order to get the next number in the term. So one of the things that this involves is is knowledge that we need to have of something that has happened previously. And unfortunately, one of the flaws with that has to do with that it utilizes a version of reasoning called inductive reasoning. And while it's very natural to reason this way, which again, to review, inductive reasoning is reasoning through previous knowledge. And I like to really put it as a experience or pattern. So when we've seen something, we sense something with our have some sense experience with our eyes. Um, we see something happen over and over again in a certain way and makes us think and conclude that that's going to be in the future. When you were doing the exercises from the first part of this lesson today in class or in the previous class that we had in Monday, uh, the the issue that we had was that when we're using an inductive rule, it relies upon us showing all these examples, and it just takes a single counter example to foil, um, what we're saying here. And it still may be accurate, but we can't be definitive. So, for example, we had the example of the product of two even integers always being even, and then we were giving just a couple examples, two or three examples. But I mean, the question is, would that be sufficient? How would we know that that's going to actually work out in the future? So here's a good example of something showing an example of inductive reasoning and something I've used for years and years. So it's this, is that the first crow I saw was black. The second crow that I saw was black. All the crows that I've ever seen are black. Therefore, all crows are black. Now, this is a pretty reasonable reasonable conclusion that we can come to, right? I mean, think about this. All crows are. We think all crows are black because we've never seen anything else. You have never seen anything else. I would presume. All the students I've had were in hundreds. Actually, it's a four-figure number, 1,000, 2,000 students over time. I'm really trying to think. None of them have ever reported seeing in person with their own eyes, with their own sense experience, a black crow, a non-black crow. Excuse me, a non-black crow. All the crows they've experienced are black. Now, is it possible? So we start to brainstorm. Now, I've had some barbaric suggestions over the years. For example, I had a student suggest that we could, if he could obtain a crow, and spray paint it orange, and it would no longer be a black crow. Now, that's not the same thing we're talking about, right? He's talking about changing the pigmentation of the feathers, but we're talking about the naturally occurring crow rather than one that's been artificially changed. All right. Or, I mean, and we're not torturing crows by painting them, right? That's absurd. The or the other thing to think about is, are all crows black? And you may be thinking about, well, you know what I know about the albino occurrence within species, that there are albino other things. Sure, there surely could be an albino crow. I don't think you've ever seen one. I don't know anybody who has ever seen one. Now we could start to go with all these things of I know a guy or the internet records it. AI, I'm sure could create it, but yeah, this is not something that I'm talking about that we could create. I'm talking about actually occurring in nature. And while an albino crow and other albino iterations exist, it's not something that we've necessarily experienced. So it gets really, really tricky. Can we definitively say we have that no uh, non-black crows exist, or that any non-black crows exist? Excuse me. I'm not sure. But what we could do is we could use deductive reasoning. So we could actually not live in this confusion of are crows really black because I think we agree that crows are black. Instead, we could use facts, previous definitions, or premises to draw conclusions. So here's what I mean. All crows are black. I saw a crow. Still talking about my experience, but because the rule all crows are black, therefore, the assumption I can make about the crow I saw is black. Let's talk about Gauss because we needed these previous terms, right? If I'm going to figure out what the 100th number is, the sum of numbers, I'd have to figure out what the sum of the first 99 is, right? And then I have to figure out for some first 99, I have to find the sum of the first 98. That's really, really tricky. Or what I could do is I could create some sort of explicit rule. For example, when we were pairing up all of those all those numbers from 1 to 10, we noticed that there was half as many pairs right when we paired them up, 1 and 10, etc., 9 and 2. So what we can do is that for the number of numbers for 10, we can pair them up with half the number of numbers, right? Because we're pairing. So then what that was is no matter what, that first number is going to be paired up with 1, and we can multiply by that number of pairs, and that's going to get us the total answer. So for the sum of the first 10 numbers, which was 55, right? Well, half of 10 is 5. 1 more than 10 is 11, and 5 times 11 is 55. And this is what Gauss had figured out, is once he did all those pairings, he created his own equation, and he was able to find this number of numbers, okay? So, what we can do then is we can actually we can distribute the n in the numerator to both the n and n plus 1, and we divide by 2. And here, right, is what we have with an explicit equation. Which is pretty neat because I can use this. I can find the sum of the first 100 numbers with that, right? 100 squared plus 100, and I take that and divide by 2. And very quickly, I could come up with the sum of the first 100 numbers in actually just a matter of seconds with a calculator, rather than punching in 100 plus 99 plus 98 plus 97, etc., etc. Next thing we're going to learn is what is called the law of detachment. What the law of detachment says, oops, make sure I get the word detachment spelled correctly. It says this, is that if we have statement A and a conditional statement, then we can have conclusion B. All right? So, if we're given that law, the next portion is that we're given A. A is a thing that's true. But because of that, therefore, we can now conclude B. Now, some of you guys are looking at this and trying to wonder, what are these 3 dots? And it means therefore. So this is one of those things you're probably going to get quizzed about when you come to class, to make sure that you are paying attention to this video. This is, again, one of these little tidbits within the videos to make sure that you guys are paying attention to the details. Another form of deductive reasoning is the law of syllogism. And law of syllogism is something given to us by Aristotle. It's where we have 2 premises to make a conclusion. It uses 3 subjects, each used twice. Now, we are going to discuss various properties mathematically. One of them is the transitive property, which states that if A is equal to B, and we have if B is equal to C, or I'm sorry, if A is equal to B and B is equal to C, then we can conclude that A is equal to C. Here's actually a syllogism for you guys, and this is a famous one again, citing Aristotle. So we have all men are mortal. If Socrates was a man. So we can conclude, therefore, Socrates was mortal. Now, check this out. I have 3 subjects, and they're each used twice. So I have men and man, right? It's my first subject. My second subject is mortal and mortal. And then my third subject, Socrates and Socrates, right? Used twice, and then this is a deductive argument called the law of syllogism. That's all for today's instruction. We have quite a bit to cover in class with regard to comparing inductive and deductive reasoning. I hope you guys are prepared. Moreover, we're going to do a little bit more work with truth tables, and it's going to be really an action-packed class going into our next quiz. So good luck. See you in class.